We're going to talk about related rates. Related rates is just what it might sound like. We're looking at how the rates, or the velocity or the rate of change between different things, how they are related, how they affect each other. So at one school I taught at, there was a physics teacher who was also the soccer coach, and he had a huge Great Dane named Cash. And when I say this dog was huge, it really did look like it was a small horse. It was crazy. But anyway, often that Great Dane named Cash would just stand there on the side of the soccer field, just watching, going and drooling a lot because it was huge, and that's what dogs do. So let's say that as he's panting, as dogs do, and drooling, as dogs do, it's creating a puddle down below. And that puddle is creating a circle of drool. It's a beautiful thing. And the radius of that circular drool was increasing at a rate of 2 centimeters per minute. Now, when the radius is 8 centimeters, how fast is the area of the circle expanding? Well, you see we're talking about the area of a circle, so let's start by doing that equation. So our area, we know, is equal to pi r squared for a circle. Since we're talking about how these things are going to change over time, we're going to need to take the derivative of this equation with respect to time. So we'll be using implicit differentiation right now. So the derivative of A is dA over dt. And we take the derivative of pi r squared, we get 2 pi r. But because we're doing implicit differentiation, we also have to put dr dt. So I want to make sure it's clear what these things are talking about. So A is the area. It's not what I meant to do. Let me try that again. I have a cool pen I was trying to illustrate. Wait, here it is. So A, there we go. A is the area of the circle. R is the radius of the circle. But the variables we got to make sure we understand are dA dt, which is the rate of change of the area. So if you think about it, if a circle is growing, or if it's shrinking, either way is true. If a circle is growing, then its area is changing. So dA over dt is the rate at which the area is changing. And similarly, the radius is also changing, so dr dt is the rate at which the radius is changing. So now that we have this equation, let's go back and look at the problem and see if we can sort out what they've given us. So they tell us that the radius was increasing at a rate of 2 centimeters per minute. So what that tells us is that dr dt is equal to 2, because that's the rate at which the radius is changing. And then they say when the radius is 8 centimeters. So that's not talking about a rate, that's talking about an actual measurement. So that tells us r is equal to 8. So they're telling us the radius is 8, but it's changing at a rate of 2 centimeters per minute. And then they ask us how fast is the area expanding. So they're asking us what is dA over dt. That's what we're trying to solve for. Well, if we plug in the radius they told us, which was 8, and the dr dt, which is 2, we can multiply all that together and get 32 pi. And since we're dealing with centimeters and area, those would be square centimeters per minute. So the rate at which the area is changing is 32 pi square centimeters per minute. Okay, so here's a similar problem. A spherical balloon is inflated at a rate of 10 cubic meters per minute. Find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3 meters. So I gave us here the volume equation for a sphere, and also my poorly drawn S, that's standing for the surface area equation for a sphere. So since we're talking about rates, I'm going to go ahead and take the derivative of both of these equations. Since we're using implicit differentiation, we'll write this as dv dt, and then 3 times 4/3, we get 4 pi r squared dr dt. And then over here, the derivative of the surface area is ds over dt is equal to 8 pi r dr over dt. So now that we have our equations and their derivatives, let's try to sort this out. A spherical balloon is inflated at a rate of 10 cubic meters per minute. So this is a rate. I know that because it says per minute, so we're talking about its change over time. And since it's just talking about the amount of air, and also I know this because it says meters cubed, that tells me we're talking about the volume. So this is telling me that the volume is changing at a rate of 10 cubic meters per minute. So that's dV dt. dV dt is 10. Now it's saying find the rate at which the surface area of the balloon is increasing. So what we're looking for, what we're trying to find, is ds dt. When the radius of the sphere is 3 meters. So that's just telling us r equals 3. It's not the rate at which the radius is changing, so it's not dr dt, it's just the radius. So when you're doing these problems, I would recommend making sure you have your equations and then going through and writing down what's given and what's being asked for. So we were given that dV over dt is 10, and we were given the radius is 3, and we were told to find the rate at which the surface area is changing. So now let's plug in what they gave us to see if we can find out that rate they're asking for. So I know the radius is 3. But we run into a problem. We need dr dt, but they didn't tell it to us. So now we've got to think, okay, did they give me information that would allow me to find dr dt? Well, if you look back, the piece of information they told us that we haven't used is dV dt. They told us dV dt is 10. So let's switch over here and see what we can learn from that. dV dt is 10, r is 3, and so we see in this other equation that we can solve for dr dt. 3 squared is 9 times 4 is 36. So I get dr dt is equal to 10 over 36 pi. Now make sure you note I am putting pi in the denominator. Pi is not out to the side, it's in the denominator with the 36. So that's my dr dt, so I'll put that over here. And now I can solve for the rate at which the surface area is changing. The pi's will cancel out. So I get 8 times 3 times 10 all over 36, and I get 6.667, and this would be square meters per minute. I know it's squared because it's area. Volume is always cubed, area is always squared. Lengths of any kind are just normal, not squared or cubed. So that allowed us to find the rate at which the surface area of the sphere was changing. Okay, so I'm sure you cannot ever imagine this, but some people, believe it or not, are really obsessed with their phones. Pretty much, they can't stop looking at them, ever. People run into signs on the sidewalk. They get hit by cars. All sorts of terrible things because they can't look away from their phone. So a true tragedy could happen here when they bought ice cream, but because they cannot stay off Snapchat and taking screenshots to actually keep it so it doesn't disappear, it turns out their ice cream is melting, and the radius of the ice cream inside their ice cream cone was decreasing at a rate of 0.5 centimeter per minute. So I'm going to pause right there. Let's go ahead and write what this tells us. The radius was decreasing at a rate of 0.5 centimeter per minute. So since it's the rate at which the radius is changing, we'll say dr dt. Since it's decreasing, we make it negative 1/2. Then it says the height was decreasing at a rate of 1 centimeter. So dh dt is equal to negative 1. Again, we're negative because it says decreasing. When the radius was 2 centimeters, so r equals 2, and the height was 5 centimeters, so h equals 5. How quickly was the Snapchat maniac losing their ice cream? Alright, in other words, how much of the volume was being lost? So what we're looking for is dv dt. That's the goal and what we're trying to find. So I'll need to take the derivative of this equation. So the v is easy, it's just dv dt. But over here on the right hand side we're going to have to use the product rule because we have an r squared times an h. So two variables are being multiplied together. So I'm going to put 1/3 pi r squared as my f, and my g will just be h. F prime will be 2/3 pi r dr dt, and g prime will be dh dt. The derivative of h is really just 1 dh dt. So then we do f prime times g plus f times g prime. So let's plug in all the stuff they gave us and see if we can sort this out. So they told us that r is equal to 2, dr over dt is equal to -1/2, the height is equal to 5. And then 1/3 pi r is equal to 2, and dh dt is equal to -1. That is a 2 squared right here. Sorry, my handwriting got a little off. So if we just plug all that in, we are going to try to leave it in terms of pi. That's usually best to leave in terms of pi. So with the first term I'll do 2/3 times 2 times -1/2 times 5. And I get basically -10 pi over 3. -10/3 was all I multiplied together, and I just stuck the pi with it. And then over on the second term, we have 1/3 times 2 squared times -1. So that gives us -4/3 pi, or -4 pi over 3. So our final answer is -14 pi over 3 is what is being lost in the volume of the ice cream per minute. So that is related rates. I wish you the best. Good luck with it.